first test was the hardest, right?
Sometimes. So, new section. New section. Velocity and acceleration. Here's the beautiful thing about this section. This works exactly like Calculus 1. So the way you found velocity, instantaneous velocity, how do you go from position function to instantaneous velocity? Tell me what it is.
Derivative.
Same thing here. How do you go from velocity function to instantaneous acceleration? Derivative, or second derivative of position. Same thing happens here. How about speed? What's speed related to? Position, velocity, or acceleration? Which one?
Velocity.
Related to velocity. How do you go from velocity to speed?
Absolute value is velocity.
Only, we'll find out why that's a little bit weird here. So the same things work for any vector function. Velocity is still, so if we allow the vector function to describe the position of a particle through space, which we've been doing with TNB, same stuff. It's why we're doing this after TNB. So if you're like, man, 12.4 is after 12.5, dude, Leonard, that's your math teacher. Pretty sure I'm on fingers, it don't work that way. Yeah, it's we're doing after that. So how this goes is 12.3, 12.5, and then 12.4. It's the last section, chapter 12 for us. We're skipping around just a little bit. So if we allow this vector function to describe a particle moving through space, then at any point I should be able to describe the velocity and acceleration and the speed, and it works the same way as Calc 1. If we take the first derivative of any position function, in this case we consider that to be a vector function, that will give me instantaneous velocity. It will also give me the tangent vector. Does it make sense that a tangent vector would give you the instantaneous direction and speed? Oh my gosh, that's velocity. Direction with a speed. That's exactly what we're talking about. Tangent vector is velocity. Cool, right? Same thing happens with acceleration, though. The relationship between acceleration and velocity is acceleration is the first derivative of velocity or the second derivative of the position function, just like you know and love. It's the same basic idea. Head nod if you're okay with that one. Now, speed's a little bit weird. You see, because you guys are right, for velocity to speed in 2 dimensions, we just say, well, it's the absolute value. That works fine. But here, velocity is actually what's this going to give you? What's a derivative of a vector function going to give you? Another vector function. So to find out the speed, it's not just absolute value. We have in absolute value for vectors. What's the notation for absolute value in vectors? It's a magnitude. So and that should make sense too. If velocity is a magnitude with a direction vector, the speed is just the magnitude. That's all that's happening. If you want to relate it back to the things we were doing, this is the first step in finding the unit tangent. This is the second step in finding the unit tangent. The pieces of the unit tangent give you velocity and magnitude, speed. And to put them together, you got the unit, you get direction. So if you take the tangent vector and you take away the speed, you just have the direction of that velocity. That's what's going on here. So what we're going to do right now is we're going to do one example. Let's consider that this particle is described by this function. Very straightforward, just to make sure we get our heads wrapped around this. And I want to find the velocity, acceleration, and speed at t equals 1. Everyone in class right now, how do you go from a position function, right here, to velocity? What do you do? Go ahead, please. Take first derivative. What's this giving me? When you did the first derivative, what is this? Tangent vector or the velocity at which point? Any point t. If I want the velocity at a specific value, basically what I'm finding is the tangent vector at a time. It's the same thing we've been doing, man. We're just calling it velocity now. Does that make sense to you? It's the same representation, same thing. We're just calling it something different. So if I want to find the velocity at 1, we go, okay, well, let's find our velocity. We have 1, 2, 3. What is it? What's that mean? I know it's velocity, but think about that. Is it weird that velocity is a vector? Is that weird or not? Well, does velocity has this connotation of a speed with a direction? Do vectors have a speed and a direction? They get a length representing speed. They have a direction. That's the vector idea. So in 3D, it makes sense that velocity is still a vector. That is the vector that's describing the instantaneous velocity of this particle traveling through space. It's got a direction. It's got a magnitude to it. Let's go from right here. From right here, we can do one of two things. We can go ahead and we can find acceleration, or we can find speed. Which one do you want to do? I don't really care what you want to do. Let's do speed right now because it's based directly on velocity. Here's the deal. Listen, if I want you to find just velocity, acceleration, and speed at that value, you don't have to take the magnitude of this crazy function. Just take the magnitude of this particular vector, and you'll find the speed at that value. It's very akin to the part of 12.5.3, where we said, well, when can I plug in a value? If I'm just finding at this point, plug it in here, find the speed of this guy, not this guy. Because then you're going to do the same thing, but you do a lot more work here. Does that make sense to you? Hello, yes, no? Don't fall asleep on me now. Come on. Stick with me. So, this is a magnitude and direction if I want the speed. So this was velocity. If I want speed, pay close attention. The speed at that time would be the magnitude of the velocity vector at that time. If you needed to find the actual speed function, it'd be a scalar function. It would not be a vector. You'd find the magnitude of this piece. Does that make sense to you? The speed function would have t's in it still. You'd have to find the magnitude there. If you want just the speed at a time, well, plug the time into the velocity, then take the magnitude of this. It's much easier. So magnitude of this vector gives you, well, let's see, square them, add them, square root them, square root 14. Square root 14 units per second, whatever we're talking about. Notice how it doesn't have a direction, though. It's just telling us the magnitude of that vector. That's what it means, the speed. That's all we're talking about. Show of hands, feel okay with that one. Let's go ahead, let's do one more. What's the other thing I'm asking you to do here? Look, we're going to run into the same situation of if you plug in a value wrong at the wrong spot and try to go with that, it's not going to work. For instance, please pay close attention because I want to make sure I hit it one more time, okay? You can plug in t here and find the magnitude. It will give you speed. But you can't plug in t here and try to find acceleration from here. Because if you try to take a derivative right now, what are you going to get? It doesn't work. So you can't plug in values and take derivatives of them. You can plug in values and do magnitudes or cross products like we learned last section. So to find acceleration, from right here, just take another derivative. Go for that, and then you can plug into 1. What's the first component?
0.
Then?
16.
That right there gives you acceleration of this particle at any point along the curve. To find a specific value, we just got to plug in a t. So if I want to figure out acceleration at 1, we got 0, 2, 6. That's acceleration. Show of hands feel okay with that one. Easy, medium, hard, what do you think?
Easy.
Any comments, questions at all before we continue? let's practice one just slightly harder. Let's go through, and I want you to do it on your own. I'm going to give you about 2 minutes to do this, okay? I'll probably be walking around the room as much as I can, there's a lecture hall here, to give you as much help as I can. But I want you to find, for this next vector function, the formula, so the expressions, the vectors for velocity, for acceleration, and for speed. Do them in whatever order you want. I really don't care. But I'm not going to give you a value to plug in. So I want to make sure we can work through it and get functions in terms of t. Make sense to you? So try all of these things, velocity, acceleration, and speed, for this. Velocity, acceleration, speed. Go for it. When I come back up here on the board, I'm going to move pretty fast. A lot of good work so far, a lot of good first steps. What is your first step, by the way? Thanks, one of you. Good job. Appreciate that one. Too busy to talk. Yeah. Derivative for
Velocity.
Get the same one there. You know, at this point in your math careers, I don't care how fast or slow you do derivatives. I really don't care. I'm focused more on the concepts. Do you understand the relationship between velocity and position? Do you understand the relationship between acceleration, velocity, and position, and the magnitude? Why speed is a magnitude? How you do derivatives, I really couldn't care less. I just want them right. At this point, Calc 3, man, we're not learning differentiation techniques until we get to some part of Chapter 13. We do partial derivatives. That's one of the last ones we talk about, okay? But here we go, man, all I want you to realize is that velocity is essentially the tangent vector. It's giving us the heading, where it's headed, along with a magnitude. That's velocity. Bless you. I just don't want you making mistakes like chain rules, stuff like that, like negatives, like square root things. That would be a bad thing. So that right there is hopefully what you have for the velocity function. I'm not plugging anything in, but that's given us right there the heading and speed. So this combination, this velocity at any point along the curve. Head nod if you're okay with that one. Now you have a choice. You can go right to speed or you can go to acceleration. I'd probably do acceleration because it's on my mind. Got an additional derivative to do. So to get from velocity to acceleration, just an additional derivative. So we'll have this. I'll write a little bit bigger to fit that there. Hopefully, unless I made a mistake. Did you guys get the same thing that I got? So maybe if you wanted to keep that as an exponent, that negative 1/2 might be a little easier to see. We multiply by negative 1/2, subtract 1 from it, becomes negative 3/2, move back down, you get this 3/2. You can make this square root of t to the third. I really don't care, as long as we understand the idea behind what's going on. Are you able to find velocity, acceleration? Show of hands if you are. Now we can find at any value t that I want. The hard one, the weird one, the hard one is actually speed. Because what speed does is takes a magnitude of which one? So if I want speed, we got to take the magnitude of this guy. Magnitude in your own words. How do you find magnitude of any vector ever? What do you do? Square them?
Add it, square root.
So when we square them, I'm going to show you all the work here. When we square them, it's this squared plus this squared plus this squared. That's the idea. That's all there is to it. Now we got to simplify it a little bit, but that's pretty much the idea. Now some things get a little nasty in here. I want to show you how to handle them. This whole thing gives us 1 over 4t. Can you verify 1 over 4t? That's squared. Plus 4t squared, that's not too bad. Plus 4e to the, when you have exponents raised to exponents, we multiply, we got 4t. Are we okay with that at least? Now, these fractions inside of square roots, they're not so much fun, okay? Especially if we have to start doing other things with this. So we're going to get rid of this. Here's how to do that if you're forced to, if you have to do it. Be smart about your common denominator. For instance, I wouldn't make the LCD 4t because I can't take a square root of 4t. I can take a square root of 4t squared. So even though that's not the L, it's still a CD. Something that I can actually use. Does that make sense to you? So I'm going to go up a power here just so that I can get a common denominator, and then when I separate the fraction, I'll be able to take a square root of the denominator and get something nice. Make sense? Or no?
Yes.
If I make everything over 4t, it's not going to help me at all, because the square root of 4t is not nice. It's 2 root t. I don't want a root t. So what I'm going to choose, it's not really an L, but I'm going to make everything have a denominator of 4t squared because the square root of that actually works. So multiply here by t over t, 4t squared over 4t squared, 4t squared over 4t squared, and what we end up getting is this thing. Now that we have that common denominator, we can put this together . And this allows you to separate the fraction, and at least you have automatically rationalized your denominator. You don't even have to worry about it if you found the appropriate LCD, if you will. So the speed function, it's a vector function. It's a scalar function. There's no vector here. We have a square root of numerator all over. When we take a square root of the denominator, we get 2t. That's at least a little bit easier to work with. Do you have to? I don't know. It depends on your teacher. Do you have to? For me, I'd say that's probably pretty nice. If you're plugging in numbers, then no, you don't have to do that. You just plug in a number. It's fine. In fact, if you're plugging in numbers, you do it here and find a magnitude. So it'd be a lot nicer. So if you're required to do it, that's how to do it. That's how to make a better choice for your denominator. Head nod if you're okay with that one. Now we're going to step back in time a little bit. I showed you how to do something. We started taking derivatives of vector functions. I've explained fully what these things mean to you. But we also did integrals of vector functions, and I wasn't really able to. I said a blurb about it. If you go back and you look at your notes, I said a blurb about what we're doing, what integrals actually do. And I said, well, area under a curve, not yet. Not yet. We talk about that later, okay? But we did talk a little bit about, well, going backwards from derivatives, doing these antiderivatives, an integral as an antiderivative, and what that means. Well, now I can really flesh that idea out a little bit. Let's say that I give you this information. I say, I know that we have a particle, and a particle started at this point in space. With that point in space, I can give an initial vector. Does that make sense? Because every vector can be defined as a position vector by doing just the terminal point. Very easy. So if I have a point in space where something starts, and I say, and I know I shot it out of a cannon with this initial velocity, if I have those two pieces of information, and I know it's like, let's say I have an acceleration curve for it, and that's saying a lot, okay? You'd have to do a lot of work with that particle to actually get this stuff. But if I know its acceleration, and I know it started with this speed, with this velocity, and I know it started at this point, we can go back and actually create a vector function for it. That's how we generally use integrals right now in this stuff, and we've already done it, so this will be fully recapped, okay? But now we're going to do it in the context of acceleration, velocity, and position. Does that make sense to you? We're going to go back and kind of redo one of these problems. It's just going to look a little bit different. Instead of giving you like a second derivative, I might give you just what? Might just give you acceleration. So because it's recap, we're going to move a little bit quickly through this. But obviously, if you have any questions or anything, just stop me, let me know. My job is to make sure, look, my job is not to be up here crushing math as fast as humanly possible. That's not my job. Otherwise, we'd be done already, okay? My job is to make sure you understand it. That's my job. So if I'm not doing my job, you got to let me know. Like Leonard, well, actually, it's Professor Leonard to you, all right? Dr. Leonard, I didn't go to evil, whatever. But let me know. Let me know that you do understand this, and then we move on, or not. Sometimes we just get in the habit of, do you get it? Yeah. Do you really? No. But I don't care anyway, because I'm bored and I want to go home. That's not a good way to learn math, okay? My job is to make sure you actually leave here understanding this concept, okay? So let's make sure that we do on this problem. So let's say that we're given an acceleration curve, an acceleration vector function. Looks a whole lot like a hyperbolic cosine, actually. Interesting, like the catenary curve. It's actually on a plane, because there's not even 3 components up there, there's just 2. So that looks a whole lot like 2 cosh. 2 cosh t is what that is, actually. Unless my memory is certainly wrong, but I'm pretty sure I'm right. And let's furthermore say that I've got a velocity at t equals 0. What is a velocity at t equals 0? What is that? It's an initial velocity. Let me make a case here that the initial velocity should be a specific vector, all right? Because if it's not, if it's got t's in it, why in the world would I even give you that? Because if you already have a velocity function, then there's no need to give you an acceleration function if we're trying to get velocity from it, right? So it's going to give you a specific velocity. It's also going to give you a specific initial position as a vector. Keep in mind that an initial vector is an initial position. Its terminal point is a point out there in space. So we're actually given an initial position from here. So we can go from acceleration to a position function or a velocity vector function, provided we're given some initial conditions here. You with me on what I'm talking about? Can you see that this problem is basically identical to things that we've done before? Yep. I could define this a little differently. Tell me how. Oh, good. That makes me feel very confident that we
R
understand
double
this.
prime, double prime of P.
I could give this as what?
R prime is 0.
R prime of 0. And then we've done the problem. Same type of problem. Now we're going to go through it just to kind of have it in this context. But this is exactly the same thing. How do I go from a second derivative? That's acceleration. How do I go from second derivative to first derivative? What do I need?
Integrals.
Integral. And then how do I go from a first derivative, which we're going to use this at that point, how do I go from a first derivative to position?
Integrals.
So we're going to have to take two integrals, and we'll have some plus c's we're going to have to deal with. So let's go ahead and set this thing up. We're just going to look at it in terms of velocity and position instead of just second derivative to first derivative to original vector function. So here we go. How we go from acceleration to velocity. Velocity is the integral of acceleration. Why? Well, because to undo that second derivative and get the first derivative, I need an integral. I need an antiderivative. So if I do this and say, let's take the first, or the integral, sorry, not first integral, the integral of acceleration, that looks like the integral of e to the t I plus e to the negative t k dt. You didn't like seeing all those e to the t's until right now, huh? You're welcome. See, I'm a nice guy. It's the beginning of March, so I wanted to be nice. I don't know why. Is that a thing? Let's make it a thing. On March 4th, you got March 1st. Is it the 1st today?
Yeah.
Good, because that's the thing. On March 1st, you got to be nice to people and wear cool black shirts. It's still in style, right? A little bit? I don't know anymore. I'm not very fashionable. I'm getting lost in I'm getting self-conscious about what I'm wearing. Let's get back to the math. Okay. Do you understand the idea here that if this is a first derivative and that's a second derivative, do an integral, it gets rid of one of the derivatives. Now, let's go ahead and do that. Right-siders, you take the first piece here. What's the integral of e to the t? E to the t. Geniuses, all of you. What else?
Minus.
No.
Oh, wait. Oh, I.
It's still a vector. It's still a vector function. And then middle people, you get the next one. What's the next one?
Negative e. Okay.
Left-siders, you get the last part. Oh, dear. Uh-huh. It's not a definite integral, right? So we have a plus c, and that plus c is a vector. I proved it earlier. So this is a plus c, the first one, because we're going to have a couple, plus c1. Keep in mind, you're doing u subs in your head. You're basically undoing chain rule in your head. That's fine to do. I don't need to see a u sub every single time for these. I don't care. I don't care.
Oh.
What I do care about is that our velocity function is now e to the ti minus e to the
Negative t.
negative tk plus c1. And now if you're okay with that one. Now, since we found velocity, that's awesome. It's also even awesomer that we're given an initial velocity, because what this initial velocity does for you is allows you to solve for that c1. We've seen it before, but here's what this says. It says when you plug in 0 to your velocity function, boom. When you plug in 0, you have to have this equal to I plus 2j. So what that says is when I plug in 0, let's plug in 0. If I plug in 0, I get 0, 1, I get I minus, oh, sorry. Plug in 0 again, you get minus 1k plus c1. This plugged in 0. Do you guys see what I'm talking about? Some people get confused, like, wait a minute, this doesn't look like that. I know that. That's what the C is for. The C lets you solve to make it that. So we go, okay, so plug in 0 here, and this has to equal this. So this says initial velocity. When you plug in 0, okay, I plugged in 0 to what I just found. Plugged in 0. It looks just like this. This has to be equal to this initial velocity. If v of 0 equals this, and v of 0 equals this, by the transitive property, they have to equal each other. That's a must. Now, can you solve for C1? Let's do that. If we do, don't waste time about it. Just don't make mistakes on it. Subtract, add. I got 2j plus k. Head nod if you're okay with that one. What do we do with that?
Plug it into C.
That's literally what this thing has to be. So, v of t, the velocity vector function here, it's this plus c1, but we have plus c1. I'm going to give you some advice before you go any further, before you start integrating again, because we're going to have to. Organize your junk, okay? Organize this stuff, because this is pretty nasty, and if we don't, you're going to have a lot of K's and J's and I's floating all around. Make sense? So let's organize this. I don't have any additional I's. So e to the t I looks really good. I have a j, let's put that in order. That's plus 2j. Also, I gave you a piece of advice earlier. You don't have to do it this way, but I like doing it this way. I always add. That way I don't have to worry about my sign errors within my parentheses. Does that make sense to you? I always add them. So what I mean by that is, if you subtract, you don't have to change the sign. Don't do that. If you add, you go, okay, let's keep this positive 1, and then you just take that minus, put it in here. That makes your sign errors a little less prevalent. If you did minus parentheses, you'd have to change the sign. It'd be e to the negative t minus 1. Do it either way. I don't care. I'm just showing you the way I do it. The way I do it is I always add when I'm combining my components. That's nicer. And then if you want to factor negative afterwards, you could do it there. It doesn't really matter. But it saves you a headache of trying to worry too much about signs. Should feel okay with that one. You always check it with distribution too. I mean, just to make sure you're right. Are we done? No. But we have a specific velocity function. No more plus c. That's really cool. What's the next step? If velocity is the first derivative, then to get back to an actual vector function, to get back to r of t, I take another integral, another antiderivative. Go ahead and do that right now. See if you can do the rest of it. I think so. Well, no, I don't think so. Got my eye. If you forget your eyes, you ain't gonna be seeing your problem very well. Nothing, not even a courtesy math laugh. I know, whatever. Just don't worry about it. I'm over it now. You just cut me deep, okay? Real deep. real deep. Did you get that? Hello, yes, no?
Yeah.
Did you? Okay, cool. How do we get rid of the plus c? If I know that my vector function is an integral of velocity, which is exactly what we have here, then when I integrate that, I get a plus c. That initial position says if you plug in 0, we get I plus k plus c2. This is 1, this is 0, this is 0, this is 1. So I plus k plus c2 says, okay, when you plug in 0 here, you get this. But you also plug in 0, you need to have this. Therefore, if I plug in 0, I get this, and I plug in 0 and I get this, these two things have to be equal. And that C2 lets them be equal. You solve for it to make them equal. Check my work for me if you would. Did you get the same thing that I got? Hello, yes, no?
Yes.
Yes. Left-siders? Then this piece just gets put right in there. I'm going to do all the work at once. If we substitute this vector, which it is a vector, if we substitute that vector here and reorganize all of our components, what we end up getting, that's in that room here, what we end up getting is this e to the t plus 2. We got a 2t plus 1. We got this whole nasty mess plus 1. And what we've done is we've created this curve that's going to map this particular particle through space forever. Pretty cool. That's how we use integrals right now, is to go from acceleration of velocity to velocity and position. So thanks for okay with this one. Last little blurb, because before kind of a fun problem. Just a little side note. We can define acceleration as a vector using t and n, the pieces that we've defined. Also, it involves curvature. The one thing that this formula does, it defines this as speed. It calls it speed, just so it's easy to work with, because otherwise this looks kind of nasty in here. So here's what this says. Find speed, take a derivative. You have to know the unit tangent. Find curvature, find speed, square it. You have to have the unit normal. And we can define acceleration as pieces. This right here, this little piece, is called it's a horrible name, tangential component of acceleration. It's almost like I'm making this stuff up, huh? I'm not, for real, it's real. Tangential, because it's part of the unit tangent component of acceleration. And this piece right here, the curvature times velocity, speed squared. Curvature times speed squared is the normal component of acceleration. Now, I want to make a case for you that this looks really nasty, okay? And it is. But watch this. Watch. If this is speed, if v equals speed, then here's what this is. Then v is actually the magnitude of the first derivative. The magnitude of the first derivative of your vector function. Did you guys buy into that? Do you guys see what I'm talking about? If that's velocity, how do you find velocity? First derivative. How do you find magnitude of velocity? Speed. Well, magnitude of the first derivative. That literally is speed. Head down if you're with me on that one. Okay. So when I'm finding the derivative of that, it's really just the derivative of that. that's what this derivative is. Does that make sense to you? So then I'm going to erase it or rewrite it. So therefore, v prime is the derivative of that nice little piece. V squared, therefore, would just equal this piece, the magnitude of the first derivative squared. Here's the point I'm trying to make out of this. We are not going to do an example. They take a long time. Okay, they take a long time. But I want you to notice something. Notice. If you were to find just the t and the n, just the t and the n of the t and b frames, they have this piece as part of the tn. You can find the derivative real easy. You now have that. Do you have this if you found the t and the n? Yeah. Do you have this if you found the t and the n? Yes. Notice curvature is part of the t and the n. Do you have this? Well, square it and you have it. Do you have the n? Yeah. These are pieces of the t and b frames. You put them together and you can define acceleration using t and n. It's pretty cool. Now, so one little side note. Again, we're not going to do examples, but if you didn't have to do the t and the n, if you just needed to do this, here's how to do it. What we would do, first derivative dot second derivative over magnitude of first t. This is real close, and I have one more thing up here. First derivative of the vector function, second derivative of the vector function is all you need. If you have the first derivative and second derivative, you dot them, divide by magnitude of the first derivative, and you cross them. Divided by the magnitude of the first derivative, you just have to find a magnitude of that. So dot them, find first derivative and second derivative. Dot them, cross them with a magnitude. This doesn't need a magnitude, it's already scalar verified. Dot products always give you scalars. Hello?
Yes.
You're just saying yes because I said hello. Dot products. Vectors?
Scalars.
Cross products. Need a magnitude. That's why that's there. So first derivative and second derivative. Dot them, cross them, magnitude of the first derivative, magnitude of that, and you can also write acceleration using t and n. Now, to me, that's like, why? Because you have to find t and n anyway. If you got to find t and n anyway, you got t and b frames. So that's the idea. Tell you what, we have you got a choice. We can go through an example here real quick, take about 10 minutes, or we can do it after a little break. What do you guys want to do? I don't really care.
Example.
Oh. You're gonna let one person choose for all of you? Let's take a vote. You want a 5-minute break, or you want to do an example? 5-minute break. Example that's going to take about 10 minutes. Like 4 of you. Fine. I want to choose. We're going to do the freaking example then. All right. So then we don't have to press stop on the video and redo everything. Whatever. It doesn't matter that I've had like 13 cups of coffee. I'll hold it together for you guys. All right? Hold it together. It's for you. I actually think this one's kind of fun. This is kind of a fun one. It does not have a lot of calculus in it. Maybe two little teeny pieces. So it's not going to be that bad. It's projectile motion disregarding wind resistance. That sucks, okay? Because wind resistance is really, really hard to calculate, especially when you got like crosswinds and different densities of air, like elevation. You fire something at 2,000 feet, you fire at sea level, it's going to behave much differently. Your air density, temperature makes a projectile behave much differently. Denser air means it's going to start losing speed more rapidly. So this is basic projectile motion, like in a vacuum. I know it's but at least it gives us a taste for what's going on. Here's how projectile motion works. It's a vector function. Bless you. I know it all looks very, very fancy. It does look very fancy. But here's what it means. Here's what it means. There's only a few things up here that we need to know, and it's not the t's. It's this. What this means, the v sub 0. It's actually kind of speed, but we call it a velocity. We need to know the alpha, what that means. We know what the g, what that means. That's only 3 pieces. So here's what these things mean. The v sub 0, that's an initial velocity. Typically, it's given to us as a speed. Honestly, like muzzle velocity, because it's already pointing somewhere. Okay, that's so typically it's given as a speed. But v sub 0 is initial velocity. Alpha, that alpha gives you an angle of inclination from horizontal. Oh yeah, h. H is the height above wherever this thing is going to, well, h is your height above a flat plane that you're, above something flat. So it doesn't have to necessarily be 0, but if we were like at high desert shooting off a cliff, our desert would act like 0. So we just call it height. What do you suppose G is going to be? Gravity. Now you're like, well, gravity, why do we even have a G? Why don't we just put like negative whatever? Well, because it depends on what units you're in. So if we have feet, we'd be using a certain unit there. If we have meters, certain unit there. So we call G as gravitational acceleration or acceleration of gravity. So let's do a quick example. We'll ask a few things about it. We're going to shoot a rifle from a 200-foot cliff with an angle of inclination of 30 degrees. That's pretty darn high if you've ever shot anything at all. From parallel to the ground with a muzzle velocity of 1,500 feet per second. So this is a souped-up 22 that's on a 200-foot cliff, like that. Okay, like that. That's what we're doing. You shoot a rifle, whatever, from 200 feet. With an angle of 30 degrees from parallel and a muzzle velocity of 1,500 feet per second. Let's identify some stuff. We are going to work through it pretty darn quickly. Let's identify some stuff. Firstly, do we have an initial velocity? Really, it's just a speed. What's our initial velocity here? Do we have an alpha? You can use 30 degrees, you can use pi over 6. I am more comfortable with pi over 6, so I always change degrees into pi over 6, or whatever the radian measure is. But you can use 30, it doesn't really matter. So angle of inclination is pi over 6 for me. Do we have a height? What's our height? Yeah, that's our height above the ground that's parallel to our angle of inclination. our G. You got two choices. You can use the 9.8 meters per second if your units are in meters. If you are in feet, what's the gravitational acceleration for feet?
16 feet per second.
That was 32.
Yeah.
3 feet per second squared. That right there is going to give you the 16 number. Okay, that's why it's in like most quadratic formulas ever. If you like drop something off a height, it's like minus 16 t squared. That's where that comes from. You don't need negative. That's taking care of the negative for you. Just 32 feet per second squared. That's what we have. So what I want right now, I'd like you to set up projectile motion and simplify as much as you can. Go for it. So set up, put the numbers in the right spots and simplify as much as you can. Then we're going to talk about what the pieces mean, do like 4 little parts to it. I'm going to just talk you through it, and that'll be the end of this section. Do you guys know cosine of pi over 6? How much is that? Root 3 over 2 times that is 750 root 3. root 3. Okay, how much is sine of pi over 6? What'd you get there? Sine of pi over 6, what is that? 1/2. Okay, so 1500 times 1/2 is 750, so 200 plus 750t. You know, whenever I'm explaining intermediate algebra, I tell them this. If you cover this up and you talk about these two things, this right there, what does that mean? I mean, they don't get this, but they get this all day long because it's a quadratic, so we can talk about this. What do these two things... Firstly, are you guys okay? Get the projectile motion, the vector. There's no k because we're just going to talk about x and y. That's all we're talking about here. But what does it mean? Well, what is the I component? What axis does that deal with? Then this gives you the distance that's traveled along x depending on how long you let it travel. That's why it's still got a t there. Does that make sense? So you shoot a gun, I mean, it's going to go that way unless you're stupid. Don't do that ever, even on the 4th of July, okay? I know it sounds fun, but don't, because it comes down. That's what happens. Gravity pulls bullets down and kills people, so don't be dumb. But if we shoot this way, the bullet's going to travel for as long as we let it travel. Right? So 2 seconds, it's going to go further and further. That's called your range. That's what that is. So the x component here is your range. Okay. J's traveling along the y component. X is going this way, that's our I component. J's going this way, that's our y component. What's that y component giving you then? Height. That's it. X is your range, y is your height. This is why, like, every time you drop something off a building or you throw something into the air in Math C, you get something that looks like that, this quadratic. that tells you how high you were when you dropped or threw something. This tells you your upward motion, how powerful it is going upwards, and this tells you gravity's going to take over after a while and pull it back down. That's what's happening. So this is your height. We're not going to spend a whole lot of time working with this, just a little taste. Number one, when would the bullet hit the ground? When bullet hit ground. Okay, well, the when is the T. Obviously, that's what we're talking about here. What's going to give us the hitting the ground, the height or the range? What's going to give us that? Height is going to tell us that. How high is something when it hits the ground? 0. So if we set y equal to 0, this would tell us that our height would equal 0. Factor, quadratic formula, whatever. I'm not going to work through it with you. When this hits the ground is around 47.1 seconds. That's a long time. It's not going to make it that long. In real life, that bullet stalls out and falls. Or it's not going to be a nice parabolic arch. It's not going to happen with wind resistance. But anyway, when the bullet hits the ground, your height would be 0. Set equals 0. These are two components. It's nice to talk about vectors because you talk about components individually. Hits the ground after 47.1 seconds. Head nod if you're okay with that one. Let's find the maximum range then. X gives us the range. Hey, do you know when the bullet's going to hit the ground? After how long? Then that is the maximum amount of time it's going to be in the air. If we take the when it's going to hit the ground and plug it into the how far it goes, we're going to get maximum range. So there's no calculus. It's just, hey, take that time, plug it into the range, and we get, I've done it for you, 61,185 feet approximately. Could you find the maximum height? Don't want to hit any aircraft, so you don't just shoot guns in the air, because that's really stupid. Let's figure out the maximum height. What gives us height? Well, the y gives us the height. If you want to find out maximum height, the way that you find out maximum height for a parabola is one of two ways. There's a calculus way, a non-calculus way. Calculus way is pretty much easier. Non-calculus way is, that's a parabola. It's a downward-facing parabola. The max height would be at the vertex. Use vertex formula, you can find the max height. Just don't take the t, take the y, okay? So the max height is you find the value, you plug it in. You can also do this with calculus. If you take the first derivative of y, well, and we set that equal to 0, we find out where the slope of the height is 0. We find out the peak. It's a downward parabola. We don't have to do second derivative test. It's going up, it's coming down. So first derivative set equal to 0. T is 375 over 16. So if we take our first derivative, this says find out where max height is. That's when the first derivative is equal to 0, or the tangent changes from increasing to decreasing. It's parabola's got to do that. Find that if we plug it in to our height. So once we found that value, we actually plug it into what gives us out our height. We get 8,000. 989.1 feet approximately. Last one, we're going to call it good. Could you figure out the impact velocity? How fast it's going when it's hitting the ground? Could you do that? actually going to be impact speed. It should really just be speed, but we call it impact velocity. So the speed when it hits the ground. What's going to give us speed? Okay, absolute value of velocity is absolutely right. What's going to give us velocity then? So if we take the first derivative of this guy right here. So first derivative that right there gives us velocity. How do you go from velocity to, because that's a vector right now, how do you go from velocity to speed? Would you want to take the magnitude now or the magnitude after you plug in the number?
After.
Do that. Let's plug it in, then we'll be able to find speed. So the velocity at, oh wait, what value should we plug in? Do we know when this thing's going to hit the ground? How long?
47.
So if we plug this in, it says, hey, velocity's first derivative. Got it, done. Take this number, plug it in here. It's going to give you velocity at 47.1 seconds. That's when it hits the ground. I'm not going to do that for you. All you got to do is plug it in. Yeah, just right there. Plug it in just right there. It's not there that he's gone. Plug it just right there, and then you find the magnitude of that vector. Do you remember how to find magnitudes of vectors? Tell me how.
Square them.
Square them, add them, square root them. So after you plug in that number, you simplify, square the two components, add them together, take a square root, absolute value, and we get around 1,503.6 feet per second, which is why this is really not super realistic, because if you shoot that gun, it is not going to gain speed ever, wind resistance wise. It's not going to do that. It can't fall faster than it first shot. It's not going to happen in this real world. So space, I don't know, maybe, but not here. Did this make sense? Do you understand the relationship between velocity, acceleration, and position? Man, we've talked about a lot of stuff. Break time, and we're done with our section. Woo.